If we take the entire software of a modern car and print it in books, we'll get 6,000 books. Moreover, when we project the amount of software for 2030, the amount of software will be equivalent to the number of books in Massachusetts science fiction library. It's understandable that building this much automotive software functionality requires a large amount of complexity. But the problem is that a substantial amount of complexity that is built up in automotive software development is accidental. It's built up because of suboptimal design decisions and unaware business needs. And we can't blame the practitioners that they should be careful in their design or be aware of their business needs all the time. Why not? Because it's impossible to make optimal decisions with intuition in highly complex systems. Practitioners need methods integrated to their development environment, which will empower them to eradicate emerging accidental complexity continuously. I'd like to reveal that there is at least 4 major areas in automotive software development that suffers from complexity. The amount of warranty cost and additional effort spent due to accidental complexity is estimated to be substantial. The first area is the source code, where traditionally have been a number of metrics to measure code complexity, but none of them can distinguish accidental complexity and recommend removing it. For example, when investigating one accidental aspect of complexity, code nesting, it turns out that 20% of code was deeply nested in one of our oldest functional areas. But we need methods to detect the complete magnitude of accidental complexity in code. The second area is architecture, where there have been methods like service-oriented architecture to compartmentalize the software services and reduce complexity. But there are 2 fundamental problems with this. The first is that services themselves can be complex structures composed of many other services. This can create dependencies between the design of services. The second is that certain services are time critical and need to be prioritized by basic software processes. These 2 problems are confined by 2 trade-offs. First, between reuse and complexity, and second, between performance and complexity. And these 2 problems are unsolved in literature. The third area is software variance, where a superset of underlying automotive software provides hundreds of software for different markets according to their needs, like different emissions, engine powers, temperatures, and so on. Variance multiply the software, the tests, the requirements, and their dependencies, and over time, they tend to grow as well. But when we analyze their sales frequency, we can see that some variants have sold in tens of thousands of cars, and other variants have sold in only a handful of cars. Moreover, sometimes engineers create variants that are very similar to each other, but because the market sectors are so many, there is never 100% communication between these engineers who could merge their variants with some agreement. And again, the problem is that there aren't methods for systematically keeping variant numbers optimal in the company. Finally, the last area is requirements where complexity causes large problems. The first and perhaps more manageable problem is the creation of complex requirements, which causes developers and testers developing the wrong functionality. The second problem, which is more troubling, is how to keep 100,000 requirements synchronized with the source code, especially whenever a requirement has several variants, which should correspond to a source file with as many variants. We need a linchpin to keep the world of requirements and source code together, and thus far, we don't have it.